Let's look now at a couple of electric field problems. In this problem, we have a proton and an electron, and they're in a constant uniform electric field created by oppositely charged plates. Why don't we go ahead and draw those plates? So here's one plate, here's the other plate. If they have opposite charges, it means that one is positive, one is negative. It doesn't say which is which. I'm just going to call this one negative, and I'm going to call this one positive. Now I'm going to add in a couple of things I know about this. I know that the direction of my electric field vector is from positive to negative. So here's my electric field. It's good to get that drawn in. I also know that my electric field will point from high potential to low potential. So this one is high potential. This one is low potential. A low potential we might have would be 0, and a high potential we might have, let's call V. So this one is 0 volts. This one could be 100 volts or 1,000 or 10,000, whatever it is. It's going to be positive because this one is bigger than this one. Okay, so now we've got our picture. We release the proton from the positive side. So let's put a proton in here. So here's where our proton starts. That's the initial point. And we release the electron from the negative side. I'll put my electron in over here. That's its initial point. When it strikes, so the proton is going to go over to the negative plate because it feels a force that's parallel to the electric field. It feels a force that pushes it to the left. So it's going to hit the negative plate. Our electron feels a force that's opposite the electric field because it's a negative charge. It's going to come over and hit the positive plate. Let's draw those motions in. So our proton is going to come all the way over here. It's going to strike this plate. That's going to be the final. Our electron is going to come all the way over here. It's going to strike this plate. That's going to be the final. So when the proton and the electron strike the opposite plate, which one has more kinetic energy? Ke stands for kinetic energy. And which is moving faster? Explain your answers. So it's talking about energy. So let's do this as a conservation of energy problem. And I'm going to stay real general at first. I'm going to get my ideas about energy, and then I'm going to think specifically about protons and electrons. Okay, so let's think about it. My conservation of energy says final energy equals initial energy plus any work done by non-conservative forces. That's work done by things like friction. We don't have any friction, so that bit's going to be 0. My final energy is my final kinetic plus my final potential. My initial energy is my initial kinetic plus my initial potential. Okay, K final then equals, let's see, my K initial, they're released from rest. So when it says released, that implies you let it go when it's not moving. So Ki equals 0. So Kf is going to be UEI minus UEF. Let's remember what potential energy is. Potential energy is charge times potential. So my final kinetic energy, and why don't I even take my Q outside? My final kinetic energy is the size of the charge. Electrons and protons have the same size of charge, times the potential difference they travel through. The proton goes from high potential to low potential, so it's got a positive charge and a positive potential difference. So a positive Vi minus Vf is going to be V minus 0, so positive charge. Oh, why don't we just start to write this stuff down? Okay, so for proton, Kf equals the charge, Q. Charge on a proton is positive of the fundamental charge. It starts over here where the plate has a potential of V minus the final potential, which we said was 0, equals E times the potential. For my electron, Kf is the charge. Now my electron, that's minus E, times the initial potential, which is 0. subtract the final potential, which was V. So minus E times minus V gives us E times V. They have the same final kinetic energy. Okay, so which one has more KE? Neither. They have exactly the same potential energy. Same kinetic energy, sorry. Which particle is moving faster? Okay, let's take this a step further, and let's remember that kinetic energy is a half mv squared. So for my next part, for my proton, one half times m times v squared. My kf is equal to E times V. That tells me that V squared is going to be 2 times the charge times the V divided by the mass, and then take the square root. This mass is the mass of a proton. For the electron, 1/2 times the mass of the electron times V squared equals E times V. V is equal to the square root of 2 times the charge times the potential divided by the mass of the electron. When we look at these two expressions, mass of the electron is a lot smaller than the mass of the proton. Therefore, the speed of the electron is going to be lots bigger than the speed of the proton. Okay, so this has a smaller mass, it has a bigger speed. Electron moves faster. Okay, so there's that question done. Let's do one more. A particle of mass 3.5 kilograms and charge positive 0.045 microcoulombs is released from rest in a uniform electric field with a magnitude of 1200 newtons per coulomb that points in the positive x direction. Why don't we draw a picture now, and then we'll get into thinking about what it is we're going to do with this problem. So our electric field points in the positive x direction, so I'm going to say positive x is to the right. So we'll draw our electric field. I'm going to write it down as a vector. E equals 1200 newtons per coulomb in the positive x direction. We take our particle, we'll just make it a little round circle. It has a positive charge. I'm going to put a plus on it. We know the mass and we know its charge. We let it go from rest in the electric field. We know that it's going to experience an electric force. Electric force is charge times electric field. It's going to experience a force that pushes it to the right. It's going to start to speed up, moving to the right. Okay, let's get into the questions. What is the magnitude and direction of the electric force exerted on the charge? Well, let's do what we just said. So electric force is equal to charge times electric field. Our charge is 0.045. This symbol mu, that's micro, it means times 10 to the minus 6 coulombs, times our electric field, 1200 newtons per coulomb, and that's in the x direction or to the right. So then our force is 5.4 times 10 to the minus 5 newtons in the positive x direction. It would be okay here to use x hat or just say to the right. Both of those are fine. So there's our magnitude and direction of the electric force on the charge. What is the change of the electric potential energy associated with the particle after moving through 5 centimeters? There are different ways to do this. You can do conservation of energy. I think I'm going to do it a slightly different way. I'm going to say that my change in electric potential energy, delta U, E, is equal to my charge times delta V. To find my delta V, I know that EX is minus delta V divided by delta X. That tells me that delta V is minus EX times delta X. So I've got minus 1200 newtons per coulomb times delta X, got to be careful to put that in meters, 0.050 meters. If you're wondering about the units here, we are given units of newtons per coulomb, so that's what I wrote down, but units of electric field are also volts per meter. So volts per meter, The meters would cancel, you'd be left with volts. So delta V then is minus 60 volts. Okay, I'm going to put this delta V in my expression for change in electric potential energy. Delta U is going to be my charge, 0.045 times 10 to the minus 6 coulombs times minus 60 volts. Let's just grab the calculator. 0.045 exponent minus 6 times minus 60 volts gives us a change in electric potential energy of minus 2.7 times 10 to the minus 6 joules. It's completely okay that this change in electric potential energy is negative. We know that if we release particles from rest, they will naturally move towards lower potential energy. So it being negative is an expected result. Part 3, find the speed of the particle after it travels the 5 centimeters. So this is our initial point. When it gets over here, that will be our final point. Since we've done some energy, let's carry on and let's write down our conservation of energy equation. Conservation of energy says E final equals E initial plus work done by non-conservative forces. Now, that one is drying out on me. Let me grab another one. Here's another blue. So my final energy is K final plus UE final equals K initial plus UE initial. Okay, so my K initial is going to be 0 because I release from rest. So K final is going to be UE initial minus UE final. Okay, I'm doing a little bit of math magic here. Minus UE final plus UE initial equals minus UE final minus UE initial. Okay, so what I have here is I took my minus out front, so I've got minus UEF. Minus times a minus gives us a positive. The reason I did this is because final minus initial is delta U. And I already know my delta U. Okay, so let's keep going. K final equals minus delta U equals minus a minus 2.7 plus 2.7 times 10 to the minus 6 joules. This is good that our K final is positive because we know we're going to have to do a square root to get to the speed. So 1/2 times m times v squared equals 2.7 times 10 to the minus 6 joules. So v squared is going to be 2 times 2.7 times 10 to the minus 6 joules. Divided by the mass, that was 3.5 grams. And then to get to my v, we have to do the square root. So let's just do that on the calculator. 0.0393 meters per second. So there's the speed after it's moved through that 5 centimeters.